Hello everyone. Today I'll talk about the solution of the problem minimum number of removals to make mountain array. To solve this problem, an easy observation that we can make is that in the definition of a mountain array, we are told that there exists some special index I. And it's quite natural to think about solving this problem by considering every possible index I and seeing what is the least number of removals to create a mountain array, with that index being the top of the mountain, as it were, and then taking the minimum over all of those. We can of course try to do it in n squared, where we'll calculate the result for every position in linear time, and that's one approach, but we want to do something better. And to do something better here, we want to pre-calculate some values for all the indices that will allow us to, just by looking at those values, calculate the answer for the given index. First of all, what we can notice is that there are two very similar and separate conditions. They are separate because, of course, they are separate. They look at different parts of the array, and they're similar because essentially one is the same as the other, just looking from the other direction. So we can only focus on one condition and then do the same thing for the other condition and combine them together somehow. So let's look at the single condition. We want to have that the elements that are left in the array up to the position that we choose, up to the ith position, should be strictly increasing. So the question is, what is the longest such subarray that we can create? Subsequence, because it doesn't have to be continuous. And this is a well-known problem. This is the longest increasing subsequence problem. So if you're unfamiliar with how to solve that problem quickly, because it can be solved in n log n, so that's the quick approach, then it's essentially a prerequisite to solving this problem in n log n. And it's a very well-known problem. It's good to know how to solve it. There is of course a problem that you can practice on LeetCode that essentially asks you to implement it. So I won't delve into my implementation of the longest increasing subsequence here. But knowing that, if we can calculate for every position the longest increasing subsequence up to that position from the left, and the same thing looking from the right, it would have to be the longest decreasing subsequence, but that's the same thing as reversing the array and taking the longest increasing subsequence. Then how do we calculate the final result from it? Well, here is the implementation for longest increasing subsequence. This is essentially the patience sorting algorithm. So we have this DP list. At first it's empty, and at every point we binary search our current value, the next value on the list, and either replace the appropriate position with the value, or we append the value to the end if we, by binary searching, reach the end of the array. And the position at which we end up with our value is the length of the longest increasing subsequence that ends at that value, so we add it to the result, and at the end return the list that will for every element tell us the longest increasing subsequence that ends at this element, not counting the element itself. We'll calculate those for left and right, so this will be the longest increasing subsequences for every prefix of nums, and for every prefix of reversed nums, and that reversed again, this is the longest decreasing subsequence on the suffix, so starting from I. And now our options are, for every position we want to know the longest increasing subsequence, and the decreasing subsequence starting at that position. And also we're only interested in values where both of those are non-zero because of our definition, because notice here that in this definition the index I cannot be 0 or the length of the remaining array, which means that there has to be at least one smaller element to the left and at least one smaller element to the right, which means that both L of I and R of I have to be non-zero, so you can write it as their product being non-zero. So that's a mathematical trick, not very difficult. So when you see A times B compared as a boolean, that means just that both A and B are non-zero. And finally, the maximum of all the options is how many elements we can keep both to the left and to the right of a given position. We of course can keep the value at that position, and all the others have to be removed. So we have to remove n minus 1 minus the maximum to get the mountain array. And that's the whole solution to this problem. This is an n log n solution because of our longest increasing subsequence being implemented in n log n due to these binary searches within a loop. Of course, you can also implement a simpler solution using a more straightforward DP, this will give us an n squared solution to this problem.